Good noon to everybody. So we'll start the second lecture of Samo about some particle ID.
Okay. So while we are gathering, this is just a video simulation of one event in the detector that we will discuss later. So the muon comes here, and then it actually hits the aerogel and makes the Cherenkov ring here. It's basically reflected from the side mirrors. And then it also interacts with the other Cherenkov detector at the time of propagation, where actually within the quartz, the photons propagate to one side. So later we will discuss these two detectors so that we don't lose time later to watch this video. I just put it here because today we have more ambitious, I'm afraid, plan. So hopefully we will come through with all that we have. Okay, so I think I have to click again here. So this is actually where we ended yesterday. And what is remaining are Cherenkov-based PID. These are really dedicated PID devices. And we already started yesterday with some properties of Cherenkov light, namely the threshold. So it's the speed of particle needs to be higher than the speed of light in the medium, and which is explored by the threshold Cherenkov detectors. And the other one is Cherenkov angle. It's a shock wave phenomena, so it's easy to calculate what the Cherenkov angle should be for the certain velocity, which translates in the momentum. So if you imagine you need some 3D imagination, you can rotate this picture around the track velocity, and then these photons will actually leave the track in the form of cone. So they go all around the track, and when imaging, this actually produces the rings on the photon detector. So now just few examples of Cherenkov angle. This is for the aerogel with a refractive index of 1.05, typical for the imaging, and you can see the pion Cherenkov angle. The maximum, the saturated Cherenkov angle, is basically when the beta particle is, when the beta is basically 1, and then you get the cosine theta Cherenkov 1 over n. So many times, loosely speaking, Cherenkov angle many times means actually this saturated value at the end. So here it's about 310 milliradians. And you can see pions at about 0.4 GeV start, and then reach saturation. Kaons start at about 1.7 or so GeV, and protons about 3 GeV starts to produce Cherenkov light. And then when they become, the two angles become too close due to the resolution of the detector, of course, we start to lose our efficiency. In this regime here, detectors work, also imaging detectors work in more or less in threshold mode, but then beyond the threshold, they can still explore, due to the difference in angle, the better resolution. This is another example from LHCb reach. They have also aerogel here, and they also use gaseous detectors, which have a much smaller Cherenkov angle, about 50 milliradians, or you can see 53, 32, or even less if the other gases are used. So the other important number is the number of Cherenkov photons. This was the question yesterday. And basically, it depends on the sine square of Cherenkov angle. It's basically a dipole radiation phenomena, which happens because the polarization is only behind the track, basically behind the wave in this case. And then this change in dipole momentum of the medium produces Cherenkov light. So it's dipole radiation and has the same angular dependence as dipole radiation. But since it's coherent, because there are many dipoles radiated along the path with a certain fast delay defined by the speed of the particle, then you get basically interference at this Cherenkov angle. And at this angle, then the output is actually proportional to the square root of the sine of the other parameters that it depends, the other constants, and also the charge square. So at the end, one can basically write that the number of photons per energy, this is now the visual light energy, the photon energy interval, and the length of the path is about 370 times the sine square of the Cherenkov angle. So it's then easy to estimate the number. Just a reminder, here is basically a spectrum around the visible light of the electromagnetic waves. So these are the wavelengths. Some detector work at the UV and some more in the visible light. And these are the energies of the photons in this range, so few electron volts. It's easier to speak in the energy because it's basically constant. Distribution is basically constant in the energy spectrum. When you translate this to lambda, so to the wavelength, actually it gets this typical dependence 1 over lambda square, which means that there is more photons in blue, a part of the wavelength spectrum, than in the red. So it means that also detectors should in principle be more sensitive in this area. The other nice things that are also explored, as we saw already, one example in the time of flight is prompt emission. And one should not forget that the light is polarized in the plane of track and the photon direction. So when you simulate, basically you have, this has to be taken into account. Now an example of number of Cherenkov photons. So typical energy range is about 2 electron volts efficiency in the visible and near UV region, and typical the photon detection efficiency over this region, let's say about 10%. So if you put this into our formula, you get about 74 photons per centimeters multiplied by the sine square of the Cherenkov angle. And now for the saturated rings, basically this sine square is 1 minus cosine square, and cosine square is 1 over n. So you get this formula. And putting in, let's say, the glass, which is roughly square root of 2, 1.4 refractive index, then you get about 37 photons per 1 centimeter of glass detected in principle in your detector. So for the solid or liquid radiator, a short distance is already enough to get enough photons. Now in the gas, basically for 1 meter of gas with a refractive index of 1.001, which is somewhere in the middle of the range, you can see some refractive indices. This is actually n minus 1 times 10 to the 6. So this, what is calculated here is in between these two, somewhere, yeah, close to this one. And what you get for 1 meter length is then about 15 photons. So you see that for the gaseous detector, you need a very long radiation length to get a reasonable number of photons. Then for the aerogel, this is an approximation of this for this small n minus 1. And for the aerogel, if using the same approximation for 1 centimeter, one gets about 7 photons. So again, you need few centimeters to get a reasonable number of photons out. So there are three types, as we discussed: threshold detectors, rich types, imaging, and internally reflected Cherenkov light. So we will start with one example of threshold Cherenkov counter from the Bell experiment. It was based on the aerogel. There was a block of aerogel with different refractive indices aligned with the kinematics of the event, and with 2 mesh type fine mesh PMTs, because there is a strong magnetic field, and this is one of the detectors that reasonably well works in the magnetic field. Now the threshold range, as maybe you remember yesterday, they were tagging kaons with kind of a 1 GeV approximately range, and these go in the forward direction, so there is a higher refractive index. And then in the 2 particle decays, the faster one goes in forward direction and slower one go in backward direction, and faster one needs a lower refractive index. So this is this point here, which makes the range from 1 to 3 approximately the difference between the point where the pion starts to radiate and the point where the kaon starts to radiate. And when you use the higher refractive index toward the backside, then this shifts to the lower momenta and even lower for these forward tagging kaons. So this was the design of one of these detectors. And then this is the expected photon yield, basically. So you can see the range for this high momentum region. And you can see then the number of detected photons for kaons and pions. You would expect basically 0 photons, but of course, detectors always have some side effects, like you can have a very high energetic delta electron in aerogel that would produce light, even though the particle was below the momentum to radiate, or your particle can hit the photon detector window and produce Cherenkov light there, which will again fake the Cherenkov light. This you can in principle know from tracking, but if the delta electron is produced in the aerogel, this you cannot really distinguish. So there is never a perfect separation, but you can see that nicely pions are separated from the kaons in this signal. So this is the example for the threshold detectors. Now, more commonly used nowadays are imaging detectors, ring imaging Cherenkov detectors, shortly reach counters, and the basic idea was proposed by Sigino and Ypsilantis. Imagine that you have 4-pi detector, so you want to cover everything, and you know that you use a gaseous radiator, so you need basically to focus light, otherwise you get a disk of light on your detector. So if you have a source of particles in the middle at the interaction point, and then you put a spherical mirror all around the light that is parallel, let's say going in 1 phi around the track, go the parallel rays, and these rays will be focused then at the halfway, at the half of the radius, where is the focal plane of the spherical mirror. And then on this, if you put your detector here, then you will get a circular ring of Cherenkov photons produced by this particle. So this is the basic idea. And if you have the faster particle, the angle will be larger and the ring will be larger. If you have a slower particle, the angle will be smaller and the size of the ring will be smaller. Yeah. So that's the basic idea. Of course, there are different variations. As we said before, if you use the gaseous radiator, then you need a long path and you need a focusing. Typically, it's not done in the spherical way as it was shown in the previous picture, maybe segmented and so on, but typically you have at least 2 large mirrors, let's say, in experiments. So again, the light is focused and then you put your photon detector here. You may use curved focal plane to reduce the errors. The other possibility is that you have a solid or liquid radiator which produces enough photons in the short path. Then it's basically enough to move your detector further away from the radiator. This is called proximity focusing. It's not really a focusing, but since the radiation length is short, your photons actually form a narrow cone. And then when this is intercepted by photon detector, you get basically a nice ring with a certain width, which is small enough for your purpose. This is just illustration of this proximity focusing reach, few photons produced, and then the heat detector where you get the ring, and this is the track. So these are 2 main variations, and we will see examples of both of these. Now, what for the detection of photons in the reach counters, you basically detect single photons. So you need a very sensitive photon detector that is capable, which means usually in the photon detector, you get 1 electron, photoelectron, or 1 pair in the solid state detector. And then you have to multiply these to the sizable amount of charge so that you can detect with electronics. Sufficient spatial resolution is needed. So preferably now the segmented detectors are used. At the beginning, only a single channel PMTs were available, and high efficiency and low background, of course, and you want to cover square meters of area. So you need at least affordable in the sense of high experiments detector, which means millions of dollars typically, but So special requirements might be operation in magnetic field, high rate capability. Nowadays, we have several megahertz per square centimeters, very high spatial resolution, again, to reduce the high rates, and excellent timing to actually separate different bunches or different interactions within the certain event. So its selection is actually a very important part of the design of the Cherenkov detector ring imaging. This is basically a rough table of parameters of several photon detectors that are available. Some of them are suitable for single photon detection. You can see the green is without any limitations. There is a CPM, maybe you already had the lecture on that, the solid state detector, which has a very large dark out numbers, but otherwise very easily detects single photons. Then there are hybrid detectors that can be used, or wire chamber or gaseous detectors that can be used, but mostly also the vacuum detectors that can be used here. So they have a pretty high, typically pretty high efficiency. When you are operating in magnetic field, you become much more limited. So solid state detector silicon PM is okay. MCP PMT is okay if the field is axial direction, and also hybrid detectors with the same limitations are okay. Gaseous detectors work nicely in the magnetic field, but they have, in principle, problem. They only work in the far UV region. So the only sensitive materials are in that region. So we will meet some of these detectors in the different designs of the ridge detectors. So now when you reconstruct, basic reconstruction is to reconstruct Cherenkov angle. You have a track. So you know in the proximity focusing detector, you know where the Cherenkov photon was approximately emitted. And then you also measure the point when it was detected, and you have a track direction, photon detection direction, and you can calculate the Cherenkov angle. In the focusing detector, it's a little bit different because all the parallel tracks will produce rings at the same position, basically. But from the direction of the track, you know where the ring should be. Then you can again calculate the Cherenkov angle, where the center of the ring should be. So basically, we always use the tracking information to reconstruct Cherenkov patterns. Now, there are several contributions to the error in this process. One is the tracking parameters, the direction, and also the positions for proximity focusing reach. There is a basic limitation in the dispersion in the medium. So different wavelengths travel at different angles, have a different phase refractive index, different emitted at different angles, which you cannot really, you can only limit this by limiting your acceptance of your detector. There is an emission point uncertainty along the track. You never know at which point the photon was emitted. Then there is a photon detection resolution, the pad size basically, which also translates in the angular error when you reconstruct the error. So we will see an example, a little bit of this later. So at the end, this is basically a single photon resolution, which is typically several milliradians. And then depending on how many photons you detect, this will go down by the square root of number of photons. So the larger number of photons is very important to get a good resolution. You can see an example here. These are 20 hits here, and this is basically the resolution, the distribution of reconstructed Cherenkov angles for these hits. So because of the error, they are actually spread around the central value. This is now the average, just an example of the average per track Cherenkov angle. And you can see that it is nicely, you can separate the pions, the kaons, and the proton bands in this reconstruction. This is many times used as a demonstration on how well this kind of plot, how well the Cherenkov detector is performing. So now, for a different type of implementation of these techniques, the early ridge detectors actually were using gaseous detector. This was used for many purposes in the high energy physics. And by adding to the gaseous detector, by adding the photosensitive vapors of photosensitive material like this is tetrakis dimethylaminoethylene, whatever, some chemical formula which has a low enough threshold for the photon emission. And the other one is triethylamine. Okay. Needed some time to remember, but anyway, it's not important. So you can add it. The amount is limited by the vapor pressure and the temperature. So you don't want this to be to condensate in your detector. So basically, for TAMI, actually, very low concentration is allowed. So you need a very long, basically, few centimeters absorption path to get a very good efficiency. So these were early detectors based on this. They work magnetic field, low initial cost, but then it works in far UV. You need quartz window or better window, and you need a very pure radiator because the oxygen and water at ppm levels already cut in your efficiency. So there were several ridge detectors in this. They operate slow, and the gaseous detector with additional vapors actually age pretty fast. So an example, this was the omega ridge here, which was basically some kind of photosensitive drift chamber and a large mirror, usually segmented, made out of smaller mirrors, later aligned, and then get the image here. Another interesting was Delphi ridge at LEP. It was actually dual radiator to cover wider range. And you had a UV photon detector time projection or drift chamber here with TAMI. And then on one side, you had a liquid radiator, which was working in proximity focusing mode for lower momentum coverage. And on the other side, you had a gaseous radiator with the mirrors. There were many such detectors around the barrel type side of the detector, and you would get actually two possible rings in lower and higher momentum range, and to cover larger areas. So these are examples of the early gaseous ridge detectors. Later, because of the use of far UV light, basically, and other limitation, high rate operation is one of them. The gaseous detectors were slowly abandoned. The latest one was actually this cesium iodide photocathode. This is actually not the vapor, but the cesium iodide is evaporated on one of the backward cathode in the multi-wire chamber, and the photon comes in basically and hits the photocathode, produces photoelectron, and then it's amplified in the wire chamber. If you use a photosensitive material, then the whole volume basically acts as a converter. Now, there are several detectors. Also, the Hera B ridge, as we will discuss later, used multi-anode PMTs. At the beginning, we started to develop, actually my PhD, to develop cesium iodide chamber for that detector. We realized that actually the limit was about 1 kilohertz per square centimeter, and the final rate was expected 1 megahertz, even more. So we were way out of possibilities to use this detector. But anyway, some detectors installed this one, and one is Alice, which has a cesium iodide ridge. You can see there is a liquid radiator and the cesium iodide chamber here. Backside has a good access so that you can exchange aged, if necessary, aged cesium iodide photocathodes. And because the charge is spread over many pads, you get the clusters of hits when you detect your rings. But you get a nice rings and a nice separation in such a chamber. The gas is typically methane, something that allows a very high gains because you only start with a single photoelectron, and then you have to multiply it to the amount of 10 to the 5 approximately to get a reasonable signal efficiency. You cannot amplify it much more because always there is some light produced in the amplification process, and this light then introduces another photoelectron, and then it starts to self-sustain. So you run into self-sustained mode. So the gains are limited in such a detector. Now, the latest version of gaseous detectors are using this micro pattern gas detector, 6 gems. In case of compass reach, this is an upgrade, the third upgrade, basically. The initial photo detector, it's again a fixed target where you have a mirror, large mirror, actually split in two, so that photons from one side go to the upper detector, the lower side to the lower detector. And initially, everything was covered by cesium iodide multi-wire proportional chambers as Alice. But then they had a high rate, so especially in this central region, so it was quickly replaced by the multi-anode PMTs we will see later. And now also this region with a high rate was replaced with micro-pattern gas detectors. You have a cesium iodide on the first electrode, photon comes in, produces photoelectron, and then it goes for a few stages of multiplication in the gems, and then it ends up detecting there. The main problem in this development was that the ions then went back to the photocathode and destroyed the photocathode rather quickly. So to reduce this ion flow back basically was a major issue. There are some things like mesh here and some other things that actually prevent most of the ions going back. And now it seems that they installed it, and we will see how well it will perform with years. So this was basically a sort of a comeback at a high rate of the gaseous detector, but still you have to operate in the far UV region. Now, after initial gaseous detectors, things went to the photomultipliers. If you have a very large detector, of course, you have a very large lever arm. You can also use very large pixels in principle to still get a good angular resolution. So you can use single channel PMTs. These were the initial PMT photon detector. This is a 3/4 inch PMT here. And this is the Hermes Reach, which was also interesting because it used dual radiator. The aerogel at the beginning of a radiation area with large for lower momentum, and gaseous C4F10 later, and then the mirror and the photon detector here. Such a combination actually produced very large rings of the aerogel because it's very large lever arm and very large angle compared to the gaseous detector. If you have a very low multiplicity events, this is okay, because in aerogel you get only few photons on the ring, and you can see ring even if there is a very large radius. But if you have a high multiplicity like LHCb, then actually these rings are not recognizable, and you will see later they installed but then abandoned aerogel in the LHCb reach. So this was a nice example of a single photomultiplier photon detector made out of single photomultipliers. So as I said before, when we were developing reach detectors for HERA B experiment, we started with two gaseous, TAMI-based and cesium-based. And TAMI-based actually turned out would age in 1 day of the operation of the detector due to very high occupancy and rate. So it was even more orders of magnitude out of operation. Cesium iodide would actually work, but only at the lower rates. Aging was not such a big problem, but none of them actually were close to what was needed. At that time, actually, Hamamatsu came out with this metal channel plate diode structure, which allowed actually a segmented anode readout at the end. So there were multi-anode. These are very small machined diodes, basically array of diodes, where the photoelectron comes in and then basically stays trapped within one channel and goes down. So it has a very nice separation between the channels. The previous multi-anodes from Philips actually had a very large crosstalk around the pads, and this structure actually allows very limited avalanche or multiplication chain. So you are actually at the lab, you are working with this device, so you measure how well the signal is contained within one channel in this lab exercise. So we immediately grabbed this opportunity because if you have a multi-anode vacuum detector, it's very nice. It doesn't really age very much, so you don't have problems of that operation. Easy, you just switch it on and off, no gas, no purify, nothing. So once your initial investment is a little bit more, but then later, basically it works. Yeah. So as I already mentioned some of these things, one of the problems was actually that the active area at the beginning was rather low. The total size was, I think, 28 millimeters and active 19 millimeters. So if you square this ratio, you come up to about 50% or less active area. So we wanted to increase, and this was another nice thing of this experiment. This is just the schematic. So to mention, it also uses C4F10. It's fixed target experiment. So there is a beamline, and then, half of the spherical mirror. The light is focused here, but because the light, if we would only use tilted spherical mirror, the detector would be somewhere here. And this was close to the magnet and close to the more noise from the interaction. So we inserted another flat mirror just to image the detector site on this side on top of the A-reach. It was more compact this way, and also the detector was out of magnetic field and the main part of the products from the interaction. As I mentioned, the active area ratio was small, so we were starting to think how to put the light concentrators. You have the two kinds, basically, imaging ones, a lens or something like that, a mirror, and non-imaging ones like Winston cones or some sort of the light guides. And with a single channel, it's easy, you can use a light guide. But with the multi-channels, actually the edge channel the light guide, in the light guide, the edge channel, it's not actually an efficient thing. So we basically slowly came to the point where we said that we will demagnify with the lens. So this was our focal plane. And if you put the lens here, you can demagnify the area here by imaging to the smaller surface of the detector. And quickly we realized that we also have to put one lens here. Otherwise, some of the photons will go out of the acceptance. And the purpose of this lens is basically to direct, from each point, direct the photons to the center of this imaging lens, so that you get a very nice, very sharp edge of the acceptance. In this case, plus 150 milliradians. Cherenkov angle is 53. So this is well enough to collect all the Cherenkov photons that come from, in this case. We had a very limited angles of the Cherenkov photons on the photon detector. So this worked very well, and this is how the module looked like multi-anode PMTs, active area, these two lens system, and electronics on the back. And for low multiplicity events, you could see a very nice ring with almost no background in the back. So the detector worked very well, but typically actually the occupancy was like this, as I said, several megahertz per square centimeter in some regions. So, but even in this, actually, you cannot really recognize individual rings here, but since you have a tracking information, you can still do a very good particle ID using likelihood functions. And this is the performance as was shown already before. And as you remember, there are a lot of pions, so we needed a very strong rejection of pions, which means that also the efficiency for pions were not really close to 100%, but still very high in this region. Now, the same concept was later then used, as I said, in the compass region, where when they replaced cesium iodide detectors first in this central region with multi-anode PMTs. They actually had a system that was working in UV. In our case, we used plastic lenses, injection molded, so they cut off at 300 nanometers or so. So we were happy that we don't have to care so much about the purity of the radiator. But they already have a system pure, so they used quartz lenses to use also the more UV light sensitive multi-anode PMTs, and came up with twice as much photons, but also a little bit more of chromatic error than in our case already. At the end, the resolution is not so much different in one and the other case. So this is an example, another example of use multi-anode PMTs. And recently, you may heard that LHCb reaches actually replaced their detectors with a type of multi-anode PMTs or flat panel PMTs. So This is widely used. Yeah, here is the LHCb reach actually. Originally, the LHCb reach, if we move to the multi-anode PMTs, used hybrid photon detector. Hybrid photon detector is a combination of vacuum and solid state detector, where you have a high field, about 20 kilovolts, so the photoelectron is accelerated to a level where it produces several pairs in the silicon detector below, on the order of 5,000 or so. And this is actually a low signal, so you need low sensitivity electronics, and the chips were actually embedded inside the sensor below, and it was using electrical focusing of the photoelectrons to image on the smaller silicon sensor chip here. It worked very nicely with some problems, initial problems of the vacuum deterioration, but this was recovered later, so it worked nicely. The problem was that the electronics was in, and when they went to the higher rates, basically they couldn't simply replace the electronics, so completely replace the photosensor with multi-anode PMTs in the recent upgrade, together with the electronics. But you can see the similar configuration as the Hera-B reach. Oops. So it was kind of a training ground for the next experiments. Here is the C4F10 again, and there was initially also aerogel radiator here, but as I said, in the occupancies here, actually the rings from the few photons from the aerogel were lost. So this is another example of the similar configuration of the reach detector. Now, I will show first the proximity focusing detector, which is an example of the one that I was recently working on and still working on from the Bell 2 aerogel reach, and the prototype of sorts that we have at the lab here. So some of you are already familiar. So just a brief word about the Bell 2 spectrometer. There are basically two dedicated ring Cherenkov detectors. One is the aerogel reach, here actually split into the aerogel radiator and the photon detector plane, two disks. This is in forward direction. And then in the barrel around, there is a time of propagation detector, which uses a quartz. And in this, actually, you only see slightly the edge of the quartz because it's transparent. In this view, actually, it's not very well seen. But there is I think 16 or 18 quartz bars around. So these are two dedicated detectors that we will discuss later with some others. Just a short exercise with this detector about the resolution and likelihood to see how actually operation of such a detector works. Also of the others that we discussed basically, but I will discuss it here. So what we are using is proximity focusing aerogel Cherenkov. We actually had from the previous Bell experiment, we replaced this threshold Cherenkov in forward direction. So we got about 26 centimeters of space because we had to fit in the same, which means that we could not really put photodetector further away to reduce the angular error. So we started to test different aerogel radiators. Approximately the proper refractive index is 1.05. And if you want to have enough photons, you have to go to about 4 centimeters of aerogel, which then makes actually a very wide ring because the proximity focusing is not good enough. So finally, we came up with the idea to use two different layers of aerogel in a way, because you can actually engineer the refractive index of aerogel in a way that rings from the one and the other layer overlap on the detector. In this way, we kind of focus with the radiator instead of with the focusing system, which is not a perfect focusing, of course, but it works well enough for lower momenta and angles also, not only in this perpendicular case where it's perfect. Yeah, and you can see the reduction. This was the measurement done in the test beam reduction of the width of the Cherenkov ring in this case. So just a few words about, so there is actually 160 millimeters here and 200 millimeters from the start of the aerogel to here. What we are using later, I will show, is kind of a hybrid photon detector with avalanche detector at the bottom, silicon detector at the bottom. So if we go look at where this error actually comes from, these are the simplified formulas, but you can calculate the Cherenkov angle from the radius and the length of the, basically the distance between the radiator, average distance, and your photon detector. And then if you differentiate that, you get the formulas how to calculate the contribution of the error, which is error on the radius, which is basically your resolution of photon detector, and the error on the known length here, because you don't know at which point in the radiator the photon was emitted. So these are two main contributions, and the other one is then the chromatic dispersion, which turned out to be smaller than then. So we didn't really pay much attention to it. So the photon detector contribution actually came out to be, with 6 millimeter pads, came out to be about 8 milliradians. And if you calculate the contribution from the thickness of the aerogel, it basically scales with the thickness with some constant, and there is 4 milliradians per centimeter. So it's with 8 milliradians matches this one, which would be then perfect match, more or less. Typically, you try to match the same errors from different sources. And then you can go further to 4 centimeters, and this becomes dominant. You can see the measurement. This is the dispersion, the pad size contribution, and the emission point contribution summed in square. And then you can see basically that quite quickly the thickness of the aerogel becomes the most important. So it was clear that we cannot simply increase to get more photons, increase the thickness of the aerogel in our configuration, limited in the space that we had. So what is the optimal thickness? You can again, so per track, actually the resolution is better. It scales with the number of tracks, with the number of detected photons. Now, if you, the number of photons also scales with the thickness, basically, to the first approximation. So then you get this kind of simple formula for the total resolution of your detector. And if you differentiate to find the minimum, then you get that the minimum is roughly at 2 centimeters. So basically, there is no point going much for, thicker aerogel as this. And at this point, basically, we realize these are some measurements. This is the number of photons, and this is basically the curves that show how you expect the resolution to be with the number for different types of aerogel. Basically, what is this? This is the attenuation length inside the aerogel. Photons actually get Rayleigh scattered a lot in the aerogel. So you can, so especially at shorter wavelengths, below 300 nanometers, and this attenuation length then influences the number of photons that you detect. So you can see that actually with the thickness, it doesn't really scale linearly, but actually drops due to these very short attenuation lengths here. So at this point, basically, we measure this also, and you can see that with using different samples of 10 millimeter aerogels, we came to this minimum of 20 millimeters roughly. So this was with then only about 10 or less, more like 8 photons per ring, which is not enough because you will have inefficiencies at the end. This is a perfect case when the track goes in the middle and you have almost 100% coverage of your detector. So at the end, we end up, as I said before, with a double layer with the 2 refractive indexes that overlap, so that we kept the good angular resolution, but got almost twice the photons out of it. Now, this is just a few, just to show basically the aerogel that we use are hydrophobic. So it means that it is resistant somehow to water, and the final shape is cut out with the water jet. So we cover kind of 4 rings, and this light, actually bluish haze that you see, this is actually Rayleigh scattered light that is scattered all around. Otherwise, it's pretty transparent material. If you use a flash, especially, you get a white feedback from it, basically. So we use 2 layers, one with smaller refractive index, which is upstream, the first one, and then with larger refractive index, larger red angle later, so that the rings overlap. And unfortunately, the second one has a shorter attenuation length, but it still works very nice. So it was completed basically some time ago. As I said, for the photon detector, in this detector, the proximity focusing hybrid avalanche photon detector is used. The difference between the LHCb is that this is proximity focusing, which means that it can work in magnetic field, which has the similar direction as the electric field inside. And then it also uses the avalanche silicon detectors here to get more charge out of it and to use lower amplification of photoelectrons. So we are using at the moment, I think 6 kilovolts in the operation of the detector. So, but it can go up to 9 kilovolts or so. So the quantum efficiency is rather high, even up to 40%. So a good detection efficiency, and you can see it's more or less evenly spread over the detector. And this is how basically at the end it looks. This is photon detector disk, and there are flat mirrors around so that we collect also the light from the tracks that go at the edge of the detector. This is then reconstructed a little bit about performance. So we reconstruct Cherenkov angle to see the performance of the detector and compare with the Monte Carlo. And you can see for mu events that this is very nice match. And the angular resolution is around 13 milliradians for single photons. And we get on the order of 12 photons per track on the average. So it's enough. You can see this typical plot, pions, kaons, and protons. You can see that we can separate. And this is basically a accumulated ring in so-called Cherenkov space. So this is angle in one and the other direction with respect to the track. You can see the ring. Many times the track hits the photodetector, which produces also the signal in the window of the photodetector, which is a strong signal, but only when it hits the photodetector. And what you see here is basically sometimes some of the light in the window actually reflects from photocathode, go back to the entrance window and coming back to the photocathode, which makes this kind of a proximity focusing reach inside the window of the photomultiplier, and this makes this second ring around here. So there are several other effects, more weak, but the main actually contributions to our distribution of photons are these two. An example, this is actually a ring where this is the magenta, these are pion, both are pion rings. This magenta is basically the expectation for kaon. The blue is circle is expectation for the pion, and you can see that the pion matches better. And here you can see also the expected distribution, angular distribution for, and the measured distribution for pion and kaon. And this is actually at 3.5 GeV, 3.6, this is close to the limits of the operation. And this is at lower momentum at 2-point-something GeV. So you can see that these rings are nicely separated, and this is how it looks on the focal plane. Okay, so just a few words. I'll try to make it quick. So basically, we don't really reconstruct Cherenkov angle and then compare Cherenkov angles, but we compare the expected pattern on the photon detector. We calculate what is our expected distribution of photons for kaon and pions and make the likelihood. So we estimate the expected distribution, and then for each path, we get the average number of expected photons, which is Poissonian distribution, and we can calculate the probability whether it will be hit or not. And then for the certain hit distribution, we calculate likelihood to multiply the probabilities of non-hit paths with a 0 probability and the hit paths with a hit probability. And this makes this kind of product. So this is the 0 probability, and this is not 0 probability Poissonian. And then in the logarithmic, this ends up in the summation. So nice thing is that at the end, basically, you only have to calculate this for the paths that were hit, which are on the order of 10, not for the all paths in your detector, because the rest is actually summed up in the total expected number of the photons here. So this is the likelihood actually function that log likelihood that we at the end basically use for the separation. And this is an example typically to calibrate or to measure the capability of the separation for pion and kaons. Let's say a decay is used where you can actually, from the kinematics of the event, decide what was pion and kaon. You don't need particle ID for that. And this is D star decay. D star plus decay first decays in D0 plus a pion which has very little energy because there is very little difference in masses. And this is so-called slow pion, can be easily identified in the event, and the charge of this can be identified. And then further D0 decays mostly into kaon and pion, and the charge of these two then defines the species. If this is positive, then the positive track will be pion and the negative kaon. If P slow is negative, it will be the other way around. So with this, without any previous bias, we can then determine the efficiency. So we collect then these events, and these are pions determined from these kinematics that go into reach. And then we select, we put a likelihood whether this was a kaon, and we still get some. This is this misidentification probability. And then these are kaons that go into RH, and the probability if they're used, likelihood if they are kaons, and you see that most of them are probably properly identified. And then we get this curve, which tells you how this identifier, binary identifier, actually the ratio of likelihoods helps you discriminate. So at the 5% of mis-ID probability for pions, we get around 83% of efficiency. And with 10%, we are all close at about 97%. So you can see, we were actually a bit surprised at the beginning that we have so many pions wrongly identified. And it turns 5 minutes. Yeah, I'll try to, sorry, but I will be probably a little bit more. The main reason that we got more misidentified pions is because they decay after the tracking before entering reach. So we have a good track, but no photons. And if we don't get photons, we say this is kaon. So in this case, basically, if we know that this was the case, we don't use a reach PID, but just the DEDX of which is much better than us strongly saying this is kaon. Now, there are other possibilities at the beginning studied for the sensor that work in magnetic field, one of the silicon PM. I'm just showing because the newer detectors are looking in this direction. It's a very nice to detect single photon, but has a very large, very strong dark count rate. So you have to have a very precise timing to actually select photons that go into ring, but then you can actually detect spherical rings rather nicely. So this is another possibility. And this is another variation of the aerogel, which is considered for electron-ion collider, where actually not the radiator focusing, but the Fresnel lens is used for focusing. So this is studied now. There is a aerogel radiator and Fresnel lens, which is very thin layer like here. You remember this from maybe from cars on the back window or so. And then you can, it's not perfect, only perfect for the tracks that would go along the central line, but you can get a nice focusing then on the detector, and this is being explored to be used in the similar type of detectors. So the last part are the detectors of internally reflected light. This was used for the BABAR, the second B-factory experiment, kind of friendly competitor to Bell. And inside the well-polished prism of quartz, the light is basically reflected internally and can be propagated as a light guide. So basically the quartz is used as a radiator, but then also as a light guide. And at the end, this exits out and keeps the angular, because they are really well rectangular shape. It keeps the angular information at the end. And this produces basically the sort of the rings. Yeah, it's not really the ring, but the shape that you can predict and use your likelihood to actually discriminate between pions and kaons. And what is the advantage of this? You don't need a space inside the detector. You take all the light outside of your barrel part, and then at the end, you can have a very large detector to detect these photons. So these were the basic idea, and it worked very nicely. So they had a very good efficiency for kaons with reasonably low efficiency, very nice low efficiency, MIS-ID efficiency for pions, and this is the typical efficiency plot in this case. Now, extensions of this were studied for this super B that was not then realized. But at the end, instead of this water expansion volume, actually there was a quartz expansion volume with the focusing. Why focusing? Because to correct basically for chromatic dispersion. Different wavelengths go out at different angles, and if you use the focusing, these different colors will be focused to different spots. And you can basically then make a correlation. If you also measure the timing, you can make the correlation between the time of propagation of this photon and the position, the angle where you detect it. And then you can make a correction to get a better. You can see here, this was a very preliminary test, but you can see that basically this correction reduced the angular resolution from 7.6 to 5.6 milliradians. So this was the first time basically that both somehow the color was also measured in the photons of each detector. And the one thing, important thing is actually that the light is photons are propagated at the group velocity, while the Cherenkov angle is defined as by the phase velocity of the light. So this makes a kind of a difference. If you look here, this is actually the range that we are in, about 400 nanometers. You can see the phase refractive index. And so it changes less than the group refractive index, and we did group velocity. So actually there is more chromatic error in the timing measurements than in the angular measurements. And this is the important difference between these two, which has to be considered when you are actually trying to make detectors that are based on the timing measurement. So this is the last part. I will still need 5 minutes, sorry for that. So this is the time of propagation counter. At the Bell, when we went to the upgrade, we removed ACC also in barrel part. And then there is very little space. We cannot put expansion volume out because there are other detectors. So the detector needs to be in this space. And we cannot do really a good imaging. So the idea came to actually measure also the timing and the one dimension in position. And from combining this position and time of arrival, you again somehow reconstruct basically a pattern from different particles. It's kind of imaging in spatial and timing domain. So you can see here. Now, the timing delay is actually a combination of time of flight and the propagation of the light in this detector. And then because of this difference in chromatic, in timing, basically you want to split the colors so that you somehow can correct for the different propagation times of different colors. And also in this case, actually a mirror at the end of the bar is used. This correction is actually more important for longer photon paths because the time difference becomes much larger than for the shorter parts, which was also shown in this measurement. So that's why also in this case, actually, for the longer photon paths, photons that go in one direction without the detector and then reflects back, there is a focusing mirror to actually help to separate the different colors. This is a nice picture how the light propagates, and what is used here is actually MCP-PMT, which is a combination of vacuum device and the dynode structure made of two microchannel plates. This makes it a very fast detector with a very good timing. A timing resolution of 30 picoseconds or better can be achieved with such a detector. So it's perfect for very good timing detectors. And this is now some examples of pattern, one example of pattern measured with 3 different likelihood hypotheses. So these are the hits in this X and time domain, the black dots, and you can see if it was pion, we expect this. If it's kaon, we expect this, nicely match. And if it's proton, we expect this, not so nicely. So also the likelihood is the highest of course, not in absolute because it's negative, but highest value. So this was basically the kaon, and it was selected kinematically from the procedure as described before. and the efficiency then, and the fake probability. Here, there is a dip, actually. It's not very efficient. Why this happens? As I said before, the delay is combination of time of flight of the particle to the detector and then propagation time. And these work together. If the track is close to the perpendicular direction, then the pions, which produce larger angle, actually propagate faster and also come here faster because they are faster. And kaons propagate longer and also come here longer. But if this particle tilts to about 45 degrees, then this reverses actually. Then the pions actually start to bounce more and the kaon go more straight. And then this actually cancels a little bit the time of flight. And this makes this area actually not, unfortunately, not so efficient in the separation of these two species. Now for the end, basically, there are several developments for the time of flight type of top-like time of flight detectors. One is actually upgrade of LHCb for the next upgrade, which is torch. This would actually replace the efficiency in the lower momentum that was supposed to be covered, I guess, by the aerogel. And it would be in front of reach 2. It would be a quartz plates in which the photons will propagate as in top, and they also use a focusing at the edge. Basically, there is the detector with the focusing to split the colors, and then you can get this dispersion relation nicely separating the timing and the position, basically, so that you can get a better timing than without focusing. And they expect to get a very nice separation in this range from 2 to 10 GeV. Okay, I think I spent enough time. And we shouldn't forget on the A reach that is here. So this is the setup in the lab. We are exploring this with rock. Focusing aerogel reach, there are some parameters, scintillator counter, which produces all the triggers, so not only the ones that go through in proper direction, but if you are patient enough, you can detect also a very nice rings in this setup that we have here, which basically use the Hera B PMTs and kind of a Bell 2 radiator with the electronics. So thank you.
Thank you, Samo. Thanks, Samo, for your excellent overview of this PID. And also, I personally thank that you mentioned the Clio Reach detector, where works. That's why I could tell you what is TEA. That is in my blood.
So you mentioned about dark matter searches are possible through Cherenkov radiation. I mean, how is it possible we can detect dark matter through Cherenkov radiation?
How can we?
Search the dark matter through the Cherenkov radiation. You mentioned in the slide that dark matter searches is possible.
Can you? I didn't really understand.
Yeah, it was written in the slide.
At the beginning of the Cherenkov radiation, or
Yeah, in the end of Cherenkov radiation. Yeah. Dark matter searches and CP violation.
No, this is just the plan for the whole spectrometer, basically. Of course, we will, if we find some funny events based on the particle that we discussed, the detection, basically. So it's not direct, of course, we don't directly detect, and we don't detect, at least so far, nothing, something similar. Yeah.
So my question is, I have two questions. So one is that, what is the advantage of HPDs over normal photon detectors? Because in HPD, we are anyway using a high voltage, and then it is being coupled with a solid state detector. So what is the advantage of it? It's in slide 60.
What is the advantage of HPDs?
Yeah, hybrid photon detectors over other kind of photon detectors. I mean, SIPM. Yeah.
Basically, if you have to operate in the high magnetic field, you have very limited options. One is the gaseous detectors, which operate in UV. So aerogel is out of the question because there is no light coming out in UV. And then you have basically MCP PMTs, because they have these microchannel plates and the magnetic field that is in the direction, actually it's okay. And then you have these proximity focusing hybrid detectors. And then at the end, we also got the silicon PMs. So these were three detectors that we were exploring basically. And the standard PMTs actually do not work in strong magnetic field because the size of the dynode structure is too large. If I go to this, okay. So basically, the normal PMT in millitesla, 0.1 millitesla already has problems. In the multi-anode PMTs, about 15 millitesla has a problem. MCP PMTs can operate up to 2 Tesla or even more, depends on the structure. Yeah.
So, and one more just short question. So I think in slide 70, you were showing a likelihood function. So for the detection, for the separation basically between the two particles, like in slide 70. So basically what I understood is that we are slide 70. Yeah, we are not reconstructing the ring structure, but just counting the number of photons.
No, we are actually, what we do is we, for the certain track, let's say, we say it's pion, and then we calculate expected distribution of photons. And then from this is basically somewhere here, and including the background. And then we calculate this for pions, and let's say kaons, and then we calculate the likelihood, some possibility that, or if this was pion. And then we compare, and then we get the results. We don't really reconstruct. It's much easier because if you have a part of the ring reflected for the mirror, you don't know whether it was reflected or not. But there is only one expected image on the photon detector, so you don't have to care about things like that.
Okay, thank you. That's all.
So my question is, on slide 77, you showed theta versus momentum plot. So yeah, 77. Or then maybe on the next.
Next one or previous?
Oh, previous one, yeah, previous. Yeah, so here the electron, muon, and pion, they occupy pretty much the similar space. So
No, actually, muon is very close, I would guess. You can see actually very tiny line here. It's actually muons, but I would guess they are suppressed here. Otherwise, they would join together with pions and make a very wide band. So you identify muons in muon chambers, and you can then put the veto to plot this so that it's not here. But the pion, I mean, muon is 100 MeV. This is 140 or something like that. So it's very close in principle. But the electron is basically flat line. Yeah,
okay.
It's beta 1 way before this.
Okay. Thank you.
Okay. Thanks, Samo. And yesterday, as I mentioned to the student, after 30 years, we met in the same ACSC school. First time as a student, now as a teachers or organizer. And I hope after a few years, maybe some of two of you may be in the same position. Yeah. So, okay, with that point, I just, again, the same equals from the institute, I try to give an art collection to the family. This is all over the institute art. That collection of you.
Thank you.
For the institute art collection.
Very nice. Thank you very much.
And also the small painting from our local tribal people. From that.
Okay.
Thanks. Yeah, now we go for lunch, and then your experiment, and then tomorrow, okay, dinner we will have, but I will not like this. We will meet tomorrow, and again this discussion we will meet. Yeah.